Let's solve a problem wherein we are expected to derive the equation of motion of a rocket that ejects gas continuously. A rocket ejects a steady jet of gas with velocity u relative to the rocket. The rate of gas discharge is constant and equal to mu kilograms per second. Our goal is to show that the equation of motion of the rocket becomes mw is equal to F minus mu into u, where m is the instantaneous mass of the rocket, w is its acceleration, F is the external force acting on the rocket. To derive this equation, we will apply the principle of conservation of momentum to the system consisting of the rocket and the exhaust gas. Let us observe the rocket at a particular instant. At this moment, the mass of the rocket is m and it moves with a velocity v. Therefore, the initial momentum of the system is P initial is equal to m into v. This represents the momentum of the entire rocket before any gas is expelled during the small time interval we are about to consider. Now consider a very small time interval dt. During this small time, a small mass dm of the gas is expelled and the rocket accelerates slightly. So after time dt, the mass of the rocket becomes m minus dm and the velocity of the rocket becomes v plus w into dt, wherein w is the acceleration of the rocket at this particular instance of time. Therefore, the momentum of the rocket after time dt becomes m minus dm into v plus w into dt. Now let us determine the momentum of the expelled gas. During the small interval dt, a mass dm leaves the rocket. We are given that the velocity of the gas relative to the rocket is u. The rocket itself is moving upwards with a velocity v. Since the gas is ejected downward relative to the rocket, its velocity in the downward direction relative to the ground becomes u minus v. Now we choose upward as the positive direction, therefore the velocity of the exhaust gas relative to the ground in the upward direction becomes v minus u. Since the expelled gas has mass dm and velocity v minus u relative to the ground, its momentum becomes dm into v minus u, which can also be written as minus dm into u minus v. Total final momentum. Now consider the momentum of the rocket and the exhaust gas. The total final momentum of the system becomes P final is equal to m minus dm into v plus w into dt minus dm into u minus v. Now if we apply the Newton's second law, that is the law of conservation of momentum, the change in momentum of the system must equal the impulse of the external force acting during the time interval dt. Therefore, P final minus P initial will be equal to F into dt. Now if we substitute the expressions we obtained, we get m minus dm into v plus w dt minus dm into u minus v minus mv will be equal to F into dt. Now let us expand the terms. We get mv plus mw into dt minus vdm minus dm into w into dt minus dm into u minus v minus mv is equal to f dt. The terms mv cancel. The product dm into dt is extremely small, so we neglect it. After simplification, we get the equation m into w into dt minus u dm is equal to f into dt. Now if I divide the entire equation by dt, we get mw minus u into dm by dt is equal to f. Let's introduce the mass discharge rate. The mass discharge rate is defined as mu is equal to minus dm by dt. Please note that this negative sign appears because the rocket's mass decreases with time. And we want mu to be positive. Therefore, we are writing mu as minus dm by dt. Substituting this relation into our equation, it gives us m into w is equal to f minus mu into u. This is the equation of motion of the rocket ejecting gas continuously. This equation shows that the rocket's acceleration is determined by two factors, the external force F and the thrust produced by the exhaust gases, which is equal to mu into u. This thrust is what allows rockets to accelerate even in outer space where there is no air to push against.